Hello. In this series of programs, we're going to look at quadratic functions, and we're going to break this down into three separate programs. In this first program, we're going to take a look at the basic definitions of a quadratic function. Next, we're going to look at the properties of quadratic functions. We're also going to look at something called the vertex and how we find the vertex of quadratic functions. And that'll lead us into how do we graph a quadratic function. All right, so let's go ahead and get started in these four objectives. But as we do, let's take a little review here of some material that you've seen before. And you recall that the equations such as 2x squared minus 5x minus 3 is equal to 0 are called quadratic equations of the form ax squared plus bx plus c is equal to 0. All right, so notice here that this equation is set equal to 0. And so we can solve for x by either factoring or using the quadratic formula, which again, the quadratic formula is that x is equal to, up in the numerator here, minus b plus and minus the square root, and underneath that square root is b squared, minus 4 times a times c, and that's all divided by 2a. And so as you went along and we looked at quadratic equations, we noticed up to this point that our quadratic equations were set equal to 0. Now, in solving here, we know that we could solve this equation, the 2x squared minus 5x minus 3 equal to 0, by factoring. And so let's see how we did that. So by factoring, this gave us two factors of 2x plus 1 in parentheses times in parentheses x minus 3 was equal to 0. So we're able to factor this quadratic portion on the left-hand side of the equation into two factors. Now, by the principle of zero product, you know that you could set each of these factors equal to 0. So we have 2x plus 1 is equal to 0, or x minus 3 is equal to 0. And now we're going to solve each of these for x. And so the first equation, 2x plus 1 equal to 0, again, we subtract 1 from both sides, and so we get 2x is equal to minus 1, and then we divide. So we get x is equal to negative 1/2. Or in the second equation, since we have x minus 3 equal to 0, we just add 3 to both sides and get x equal to 3. So here the solution to this equation would be x is equal to negative 1/2 or x is equal to 3. And so that was our factoring method. We also can do this with the quadratic formula. And again, you may have learned from other faculty members in these presentations that you can, if an equation will factor, you can factor and solve, and then we can also use the quadratic formula to, in a sense, verify our solutions. Or we could have started off with the quadratic formula from the start. And so let's now take a look at how the quadratic formula would be used to solve this particular equation. All righty, so with the quadratic formula, again, we've got to recognize our a, b, and our c here. So our a is going to be equal to 2, our b is going to be equal to negative 5, and our c is going to be equal to 3. Again, that's coming directly from our formula here of the quadratic, is that we have ax squared plus bx plus c is equal to 0. All right, so then we're going to take these three values that we have here, and we're going to take them and plug them into our quadratic formula here. So once again, we previously just saw our quadratic formula a moment ago. So notice it's minus b, so we have a negative 5. So I have a minus minus 5 plus and minus the square root of negative 5 squared minus 4 times 2 times negative 3. And again, that's all divided by 2a, which in this case is 2 times 2. Simplifying underneath the radical, negative 5 squared becomes 25, excuse me, then plus we're going to have 24, and that's going to be 4 times 2 times negative 3, but there's a minus in front of the 4, so again, the minus and minus becomes a plus. And then out in front there, we notice that we have a minus 5 and minus a minus 5, so that comes out to our 5, and our denominator comes out to 4. Simplifying this down, we see that we end up with the 5 plus or minus the square root of 49 divided by 4. And again, that simplifies to 5 plus and minus 7 divided by 4. And finally, our final step is that we're going to see if we take the 5 plus 7, we'll get 12 over 4. That gives us 3. If we take the 5 minus 7, that gives us negative 2 over 4, which gives us negative 1/2. And so therefore, we see we verify our solution. Now, you might be saying, well, what's the point of all this? We're just kind of reviewing. Well, we're going to see in just a moment that as we go through the steps of graphing quadratic functions, that this review will be very helpful in the fact that sometimes we will be looking to see if we can factor or possibly use the quadratic formula. Setting the equation equal to 0 is the same thing as finding the x-intercepts. And again, we'll talk more about that as we graph functions. So let's now go ahead and define really what a quadratic function is. We've reviewed what a quadratic equation is, but what's the components and properties of a quadratic function? So here we go. So now let's change the equation that we have of 2x squared minus 5x minus 3 is equal to 0 to 2x squared minus 5x minus 3 is equal to y. All right, so now what we've done is we've said, hey, we haven't set this to a specific value of 0. We've changed that now to a general value of y. And so this gives us a broader sense of more possible solutions that would work for x and y in this equation. And so again, we've noticed that we now are solving for all xy pairs that solve the equation, not just for x when y is equal to 0, is effectively what we did in the review examples. And so this leads us into the definition of a quadratic function. So, we now have formed a quadratic function of the form y is equal to ax squared plus bx plus c. Okay, so this is in the formula where we are using y. However, if we want to put this in functional notation, which we typically want to do, we're going to have that as f of x is equal to ax squared plus bx plus c. And so now we see that we have this definition of a quadratic function. And again, basically we've taken the quadratic equations that we've had in the past that were set equal to 0, and now we've put in there y, or we've put in the functional notation f of x is equal to the ax squared plus bx plus c. All right, so now that we have the general formula, we want to take a look at some properties of quadratic functions. And we'll notice again that we're going to be solving for xy pairs, so we're going to have a set of points that we can plot to get a graph of the quadratic function that we might be interested in looking at. All right, so let's take a look at some of the different properties and eventually get to where we graph a full quadratic function. All right, so we're going to use two different functions here, and we're going to use the one we just saw. We're going to use the f of x is equal to 2x squared minus 5x minus 3. And also we're going to use the next function, f of x is equal to minus 2x squared minus 5x minus 3. All right, so notice there that the change is that the a is different in both of these. That in one, the first one, the a is positive 2, and the second one, the a is negative 2. And we'll see how that comes along. So we're going to use these to discover some of the properties of the quadratic functions in the form of f of x is equal to ax squared plus bx plus c. And so what we're going to do is we're going to graph both these functions here. Now at this point, don't worry about how I got the graph, okay? We'll get to that in just a moment. And so we've got the two functions, and we'll see the first function, f of x is equal to 2x squared minus 5x minus 3, has a graph that looks like this first one here on the left side. And so I'm going to just call this figure 1 here. Let's just label that. Okay, so figure 1 is the graph of that first function. If we take a look on the second function, when we graph that, and we'll just call that figure 2 up here, we'll see that that graph of f of x is equal to negative 2x squared minus 5x minus 3 is in figure 2. Now let's describe what happens. Notice that figure 1, we have a graph that's opening upward. Looks almost like a little bit of a cone there, right? Not quite a cone because it's two-dimensional here. It's not truly a cone. But what we have is we have a parabola opening upwards, and that we'll see in just a moment. That's the definition. And this is opening upwards, and it goes through some points there. It looks like it's going through the point 0, -3 here. Looks like it's going through the point 3, 0, and it looks like it's going through this point over here of -1/2, 0. Over in figure 2, we notice that it's opening downward, and we notice that this figure looks like it's going through the point 0, -3 here, and also it looks like it's just crossing the x-axis almost here at -1, 0. And then there's some other crossing of the x-axis almost at -1/2, 0 here. So, and then it goes down from there. All right, so what we want to do is we want to talk about these different properties of these graphs and how we can get to graphing this. We're looking at the graphs of quadratic functions. And quadratic functions have associated with them something called a parabola. And really what that is their graph. So a quadratic function in the form of f of x is equal to ax squared plus bx plus c forms a graph named a parabola. We can tell the direction the parabola opens by looking at a. Once again, a is the coefficient on the x squared term here. All right, so in our first equation, f of x is equal to 2x squared minus 5x minus 3. We're going to see that our a is going to be equal to 2. In our second equation, f of x is equal to minus 2x squared minus 5x minus 3. We see that a is going to be equal to -2. And these values are going to have an influence on the way the graph looks. And so the first figure here was the graph of f of x is equal to 2x squared minus 5x minus 3. Notice that its general shape looks like it's going up and has a low point in it. And now the second figure, notice this is the graph of f of x is equal to -2x squared minus 5x minus 3. And notice that it looks like it has a high point in it. And that's truly what's happening here. And we can determine the direction the parabola opens based on a. So if a is greater than 0, the parabola opens upward. And so that's what's happening over here in the first figure. For f of x is equal to 2x squared minus 5x minus 3, this parabola is opening upward because a is in fact greater than 0, so 2 is greater than 0, so we know the parabola will open upward. On the second graph of f of x is equal to -2x squared minus 5x minus 3, with a being -2, since a is less than 0, the parabola will open downward. And so we see that -2 is less than 0, so we have a downward parabola. And so that's going to be the first thing that we're going to look at as we're looking at quadratic functions and talking about graphs of quadratic functions. We always can take a look at the quadratic function and take a look at the nature of whether the quadratic function opens upward or whether it opens downward by taking a look at what happens with the lead coefficient on the x squared term, and that's our a. All right, the next thing we want to take a look at is notice one of the distinct things in the parabola is that it either has a low point or it has a high point, really a maximum or a minimum in there. And so let's see how we find that and the particular name of that high point or that low point in the graph. All right, so this is called the vertex. A quadratic function in the form of f of x is equal to ax squared plus bx plus c contains a point called the vertex, which is located where the graph turns. All right, so once again, I've got my two equations up here, and let's take a look at the first equation here of f of x is equal to 2x squared minus 5x minus 3. And we've already determined that a is equal to 2, so we knew that this parabola was opening upward, and we saw that just a moment ago. And we'll just mark that again. But the other thing we'll notice in this parabola, that there's this distinct area where the parabola goes from decreasing, then changes to increasing. So there's a point here that we've got to take a look at that will be the vertex and is the turning point of that graph. And so also taking a look at the second graph, f of x is equal to negative 2x squared minus 5x minus 3, we already saw from a equaling negative 2 that this opens downward. All right, so we can see that there's this distinct situation here where this graph appears to be increasing, then it turns and decreases, and so there's a point here where it changes from increasing to decreasing. In other words, the graph will turn there. So what we want to do is we want to take a look at these a little bit more and examine them and find out how we find the vertex of each of these graphs. And so we know also that by looking at A, it tells us something else about the graph, and that's with regard to the vertex. If A is greater than 0, then the vertex is a minimum. What's the minimum? Well, the minimum is a low point. Okay, so we can see that this vertex right here is the lowest point on this graph, and so right there we're looking at a vertex, and again we'll find the exact value of it in just a few minutes, but we're going to see it's a minimum. And so if A is positive, the graph opens upward, and then the vertex is going to be a minimum. Likewise, on the, there we go, there's our vertex. Likewise, on the second graph that we have here of f of x is equal to negative 2x squared minus 5x minus 3, we can look at A to determine what happens with the vertex as well. And so if A is less than 0, the vertex is a maximum. And so we can see that here in looking at our vertex, we can see that's the highest point on that graph. And so hence it's a maximum, and maximum means it's the greatest value on that graph, and that's your function will have that value. Your y value will be the largest value on the graph as you look at the graph. Same thing with the first graph. When we're talking about a minimum, the y value is the one we look at to be the minimum, not just the x value. We'll use the x to get the y value. Again, we'll plug x into the function and we'll find the minimum or maximum, which will help us to find the vertex. Okay, so what we have done so far is we've looked at the fact that quadratic functions have a particular form. Quadratic functions have a graph that's in the shape of a parabola, and we've also noticed that quadratic functions have a higher or low point in them that's called the vertex, and that to get the upward or downward picture of whether the graph opens upward or downward, we look at the lead coefficient A, and that lead coefficient A will also tell us whether the vertex is a maximum or a minimum. Now we want to delve a little bit more deeply into how do we find that vertex in this particular type of quadratic function. So here we go. The quadratic function in the form of f of x is equal to ax squared plus bx plus c contains a point called a vertex, which can be found using the following formulas. First of all, to find x, we're going to say that x is equal to minus b divided by 2a. And then once again, the a and the b that we're referring to is the lead coefficient a in the quadratic function, and the coefficient on the middle term, the x term, is our b. So that'll give us our x. To get the y, or the value of the function, we effectively plug in that x into the equation. And so here, I know this looks a little different. Basically what we have here is, I could have rewritten this as f of x, where we're letting x be equal to minus b over 2a. So here we have y is equal to f in parentheses of minus b over 2a, which is just f of x. So basically what we're going to do is we're going to find the x-coordinate of the vertex first. Once we have the value, we plug it into the function and find the y-coordinate of the vertex. A lot of books, when you read this in the textbooks and you see this the first time, their definition of this looks a little complex and almost looks a little confusing. But basically, it's just find the value of x and then plug it into the function and to get your y. We also want to make a note of another important fact. The equation x is equal to minus b over 2a is also known as the equation of the axis of symmetry. Okay, notice it's in the form of the equation that x is equal to something. Even though x in general will be a constant here, such as x will be equal to 5 or x will be equal to 3. I'm just making up numbers now, simple equations. Then we want to write it in the form of equation. In just a few minutes, as we examine the full methods of graphing, we'll see how this axis symmetry comes into play and how it looks on our graph. Okay, so let's go ahead and take a look at our function and see how we find the vertex of a function using these two formulas. Okay, so once again, we're going to be at our first example here, that f of x is equal to 2x squared minus 5x minus 3, and we're going to find the vertex. Again, we're going to find that vertex using the two formulas. First of all, that x is equal to minus b over 2a, and secondly, that y is equal to f of b minus 2a, which again, we're just plugging in that x. All right, and I've left the graph up here too, so we can look and see how this vertex comes into play on the graph. All right, so we first identify our a and our b. A is going to be equal to 2, b is equal to negative 5. Really important that you take the sign in front of both a and b here. That is a critical element of this. All right, so x is going to be equal to a minus 5, which is minus b in the numerator, over 2a. So we're going to have 2 times 2 in the denominator. And so this gives us that x is equal to 5 fourths. All right, now we don't want to panic here. We start out with an example of a fraction. And I've done it on purpose here to let you know that not all the times will you get a nice number like 5, 6, 10. You will get quite often fractions in there for your vertex in the quadratic function. All right, so we have x is equal to 5 fourths. So what are we going to do with that? Well, we're going to remember that that's also known as our axis of symmetry. And so what's going to happen there? Well, basically what happens is the axis of symmetry is, notice it's x is equal to 5 fourths. So the dashed line I've drawn in here now is where 5 fourths is on our graph. All right, and so what's going to happen is, notice that axis of symmetry splits that graph directly in half, in that the left side, if we folded this, if we looked at this graph as a piece of paper and that dashed blue line, if we folded the graph, that piece of paper with that graph on it in half along that dashed line, the left side of the graph will fold exactly over on the right side of the graph about the axis of symmetry. So symmetry means there's a balance, there's an equal half, so to speak. The left side and the right side will be the same about the axis of symmetry. All right, and then the neat thing about that is it'll give us a way of looking for points, and hopefully if we find one point on the graph, then we can use symmetry to find its corresponding point on the other half of the graph about the axis of symmetry. All right, so we want to, again, look at the fact that this is an equation, okay? The equation of the axis of symmetry here is x is equal to 5 fourths. All right, so keep that in mind as you're working through your homework problems and working with quadratic functions. All right, so next we're going to find the y-coordinate here. All right, to do that, we're going to plug in the 5 fourths. So notice that up in the beginning here, we had this fancy formula here that was a little bit scary to you maybe, the f of negative b over 2a. Well, basically what happens there is we're going to take this value of x, the 5 fourths, and we're going to plug it into the function everywhere we see an x. Okay, everywhere we see an x. And so then we're going to do the math. Okay, so here we're going to square the 5 and square the 4, so we'll get 2 times 25 over 16, and then do the multiplication. Now here again, we've kind of made an assumption that you are able to work with fractions, and so if you're having trouble with working with fractions in this type of example, please ask your instructor or go to the tutoring center for some extra help with those. And so what this turns out to be is that once we do the calculations there, we see that the value comes out to be 49 over 8. And you're saying, wow, that's going to be difficult to graph. Yes, it can be. And so what we're going to have is that our vertex is going to be 5 fourths, which is going to be 5 fourths comma 49 over 8. Our x value is 5 fourths. Our y value is 49 over 8. Or you might say, well, let me change this into a fraction and see if it makes it easier. From a fraction to a decimal. We already have it in a fraction. We're going to change it to a decimal. And so what we're going to see is that this is 1.25 for our x value and 6.125 for our y value. Now, definitely what we want to do is we want to plug these values into our calculator, but as you've seen in previous programs when you talked about graphing of any type of function, you could plug this function into your calculator and generate this graph like I've done here. And then you could use the trace feature on your calculator to locate the vertex. However, it is important that we find the vertex as we did here. And the reason I chose this example is because notice finding the exact values on the calculator by just looking at it would be rather difficult. So we have the method here of finding the exact value of our vertex. And many times in mathematics, we talk about finding the exact value of a particular quantity x and y. And so we have a method here of doing that. Okay, so let's move along and take a look at some other examples of other features here of the quadratic functions. So our second example is the second example I showed you previously. However, I've made a little change here to make it a little bit easier. And what I mean by the second example is the fact that a is equal to -2, the parabola opens downward. So to work with this a little bit better and to show you that the numbers do come out to be whole numbers instead of fractions, I've modified my example here that I was using previously to really basically change it. So here we're going to find the vertex of the function f of x is equal to -2x squared plus 4x plus 3. And I want to show you what happens here if instead of minuses in there we have pluses. So here we're going to first of all look to the fact that a is going to be equal to -2 and b is equal to 4. From a being equal to -2, we know that our parabola is opening downward, which we can see that here in the graph. But if we didn't have the graph, we can denote note that as we go along here that it opens downward, and that our vertex is also going to be a maximum. So we'll say the vertex is a max here. All right, and so again, I've got the graph. I've put the graph up here for you. Normally when you see that function to start off with, you won't have the graph in front of you. And so we can say it opens downward and our vertex is a max. All right, so let's find the vertex here. So we're going to first find x. And so once again, we're going to plug into the equation x is equal to minus b over 2a. And so we have -4 divided by 2 times -2. So we end up with -4 over -4, which comes out to be equal to 1. So everybody's saying, we're relieved. We've got x is equal to 1. Well, again, this is our axis of symmetry, right? So we've talked about that just a moment ago. So here's x is equal to 1, and so we can put a dashed line in there for our axis of symmetry at x is equal to +1. Again, that's our equation of our axis of symmetry. So we know the right half of the graph will fold off onto the left half of the graph. We next find our y-coordinate here of our function. We're going to substitute x into the function. And so once again, we have y is equal to f of minus b over 2a. Well, that came out to be equal to 1, right? So that was our x is equal to 1. And plugging that in, we get -2 times 1 squared plus 4 times 1 plus 3. All right, so that's going to give us -2 plus 4, which is going to give us +2, plus 3, which gives us 5. And so what happens here is our vertex is equal to +1, +5. And so you can say, wow, that's good, because then I can mark that really easily up here on our graph and see that particular value up there of 1, 5 as our vertex, and now we know that that's a maximum. And so we also know by looking at this value of 5 that that's the maximum value our function can ever take on. Okay? Notice this as well too as we're looking at this particular graph. If we talk in terms of the domain of this graph, the domain here, remember the domain is going to be all the values of x. And so the domain in this quadratic function is going to go from -infinity all the way up to +infinity. Again, it can take on any value of x. But the important thing here is that the range of our graph, putting this in functional notation, again, remember the range is our y's. Notice that we're capped here. Okay, notice that we have to stop up here at 5. We're not going above that, right? So that's where our vertex is at 5. And so what happens for our range is going to go all the way down to -infinity. Again, because this graph keeps on going with these arrows here, comma 5. Now notice I'm going to put the square bracket in my range. Okay, so our domain is all the real numbers, negative infinity to positive. Our domain is all those real numbers, but our range here has an upper limit here. And we want to make sure that we realize, again, I probably do a real good job putting those square brackets in here, so let me just make that look a little better here. So 5, and then we put those square brackets, there we go, on our range. All right, so that's another little add-on here I want to throw at you as we look at the graph is we can use the vertex then to help us determine the range of our function. Okay, this ends our look at the basic properties of a quadratic function. In the next program, we're going to look at how to graph quadratic functions.